Hey guys, today we'll be looking at this fundamental principle. V final equals V initial plus F net over mass times delta T. Or in other words, Newton's second law. In this video, we will observe the motion of some object that is moving at the same speed without changing direction. We will analyze the results of a tracker on a video that captured the motion of the object. We will construct a computational model that accurately describes Newton's second law. We will compare the computer model to the actual observation model using graphs of the models. In this case, the final result is that the actual model is mostly in line with the predicted model. And finally, we will discuss potential errors that would have arisen throughout this setup. Speaking of setup, our setup is very simple. We just need one tennis ball, which we will define as our system, in one table. Here, you can see a screenshot of me loading the tracker, the video of me rolling a ball across the table into tracker. Notice the axis orientation. The positive X is to the left of the origin. The origin of the axis does not change the velocity data, only the direction. No matter the orientation of the axis, the distance of the ball relative to the origin does not change, so long as the origin is centered at the ball at the start of the tracking. Now, after we load the video into tracker, we can use tracker to extrapolate data that is useful for us. From the tracker video, we can extract data such as velocity average. We will use this computational model for the computational model. We will use the computational model to compare how the ball should have behaved given absolute constant velocity throughout the time frame we're considering. In this scenario, our ball moved for 0.73 meters in a total of 2.35 seconds. Our velocity average is a change of position over the change in time. Our velocity average ends up being 0.331,0,0 meters per second. One of the simplifying assumptions that we are making for this video is that the F net is a vector quantity 0, 0, 0, or the zero vector. In order to achieve constant velocity for this lab, the net force acting upon our system must be 0. Here's our Python code that will be used to construct the computational model for our predicted motion. Note that the ball's position, velocity, and net force are all vector quantities. Python will construct a model based on the initial conditions that we set. The system's mass, we can say, is 1. Note that because the F net is a zero vector, the ball's mass does not change the model. Our ball's position is at the origin, where we set the orientation of our axis at 0, 0, 0. And our velocity vector is our average velocity throughout the entire time frame, which we calculated in the previous slide to be 0.331. Now, the interesting thing to note is that the delta t is 0.033, which is the same delta t that the video uses in between each frame. Now, using both the actual motion data and the predicted motion data, we can create graphs and compare the two graphs. The computer model predicted quite well the motion of the ball in reality. The two motions diverge slightly in the middle due to the ball accelerating in real life, due to some unknown force, or unknown non-zero F net force. Why is that? Well, can we say that our F net in our system in real life was the zero vector? No, we cannot. We just said that the ball's motion was not constant throughout the entire time frame. The motion of the ball was very close to the computational model, but not exactly. Things that might have skewed the motion of the tennis ball in real life, but is certainly not limited to, are the friction on the table acting on the ball, and the resistance of the air acting on the ball as well. With a non-zero F net, this would be an extremely plausible reason as to why the real-life motion of the tennis ball did not exactly meet the predicted results. Alright guys, that's it for this video. Thank you very much.